Okay. Hello everyone. Welcome to the first session in the scalable of the year. Third year in the running. Today we have very excited to have a speaker to give a talk on continual learning and really about test time training for infinite context. So a bit of a bio for the speaker. So Tianyuan is a PhD student at CS by the Professor Bill Freeman. His research has been about computational cryptography, computer vision, and recently on model and equilibrium. And also the scalable session is sponsored by some virtual partners and also Professor Yun. So thanks everybody for sponsoring us. With that, please.
Thanks. I'm very happy to be here to talk about some of my thoughts and my work on infinite sequence lengths for continual learning. And specific today, I will talk about two work, all related to continual learning, but very different. One is on large nonlinear RNNs. The other is about kind of like understanding RNN, how much RNN can memorize. And through this talk, I will talk about some high-level ideas and some technical details. It's fine if you miss the details, because we talk a lot about technical details, probably very fast. So to get started, let's talk about some motivations. We all know that the sequence length of the foundation models is increasing very rapidly. And the Gemini 2.5 at the beginning of the last year can already handle 1 million sequences, 1 million tokens. And such long context model already have a lot of use cases, like long document understanding, long arithmetic chains, long video generation, and etc. And it's no doubt that the sequence length will continue to increase. Probably 3 million this year, 5 million next year, 10 million next year, something like this. But I think that at one point, we probably need to jump from finite sequences to infinite sequences. And such infinite sequenceless models, we have a lot of new use cases. For example, you can use it for personalized assistants or personal agents. You can imagine a model that can see whatever you see, hear whatever you hear, from the day you are alive to the day you die. And it have you complete tasks given on that memories. And as such infinite sequence length models will also be used for word models. And another perspective now, if you can maintain effective in-context learning through infinite long sequences, this is a form of a continual learning. And if you can achieve continual learning, you can do a lot of stuff. You can put models, millions of models on millions of different environments, like models learning their environments. And basically you can have a swarm of intelligence and probably something like evolution. And it will be important for things like AGI. So how to get it? How to make infinite sequence length learning possible? I think if you look around now, there are probably 3 possible bets. One is about scaffolding around current models. And such scaffolding can be things like context optimizations, like things like context compaction, as we see in cloud code. And it can also be things like self-edits, self-distillations, where you continuously to train the model on the fly at the inference time. And I think such scaffolding will be very useful to boost the sequence length of current models. And it can be used also to synthesize new data for the future. And I think there are 2 other possible ways, but all on the architecture side. One is about sparse attention. And it will have a constant reduction on the flops. We will have typically 10 times to 100 times reduction on the flop. But it's still quadratic cost. So I don't think we can directly take us to infinite sequence length. Another bet on the architecture side that recently got kind of popularized is about recurrent neural networks. It will have constant frequency. And the major feature of the RNN, it does compression. It learns to do compression. It compresses previous history in the states. And it's a bug. It's a feature. It's also a bug because it does compression. So it's probably going to forget something, and which means it probably underperform some tasks. And there are also a lot of other challenges, not only on architecture, but also on training data, evaluation strategy, training strategy, etc. Today, I want to discuss mostly about the architecture side, and specifically on RNNs. So when we talk about RNN, we typically think about such structures. We typically think about data as coming colorly in time. And each data is typically a 3-dimensional vector. And one most important thing about RNN is about its recurrent states. And when you think about the states, you can think of it as a matrix or multiple matrix, but for simplification, you just think of the state as a matrix. And the state will be updated iteratively over time. The second most important operation of RNN is given the updated states, how to compute the outputs. So RNN just have two operations, how to update the states and how to compute the outputs. And when we think about such recursive structures, it's actually very non-trivial to train on GPU. I will talk about the challenge. The first challenge probably a lot of people can see is about parallelism. How are we able to parallelize such recursive updates on GPUs? It seems impossible to do so. But fortunately, over the last few years, there are some ideas got popularized on how to parallel RNNs on GPUs. And all of them use an RNN updates called linear recurrence updates, where the states S updated by a linear transformation. And this matrix A and B depends on current inputs. And basically this linear transformation matrix summarizes all the RNNs, all the linear RNNs you see popular today, like Mamba, Dirtnet, linear attention, etc. They just take different form of this matrix form. And the good thing is that when you think about a chain of linear transformation or chain of linear updates, it's a chain of associative operators. Linear operators are associative. And given a chain of associative operators, you can parallelize them on GPU using things like parallel prefix scan or different variants of parallel prefix scan. And all Mamba, Dirtnet, linear attention are parallelized roughly following this idea. There are a lot of details I want to go into them, but parallel prefix scan, you just need to memorize these words. And unfortunately, this idea cannot be used to parallelize nonlinear RNNs because nonlinear updates are non-associated. And that's also the reason you see popular RNNs are linear recurrence RNNs, or just linear transformation with states. The second problem GPU poses is about arithmetic intensities. So in this table, some specs of recent generation of GPUs. You can see that the speed of a mammal grows much faster than the speed of read and write and the memory bandwidth. And if you look at the recent generation, the most newest one, the time it takes to read and write one byte, you can do around 300 floating point operations on the mammal, which basically tells you on GPU, read and write are so expensive, and you should try to minimize your read and writes when you train these models. And if you zoom in on the single time step of RNN. If you zoom in at this single time step where you want to update the state, where you want to compute the outputs, it will have a ton of read and a ton of write. And it will have a very bad arithmetic intensity. It will have around the amount of compute is around 2 times the amount of read and write. And which basically says it's impossible to train on GPUs. It will be very, very slow, severely memory bounded. So how to get around this problem? And also, fortunately, over the last 5 years, people figure out a way to do so is let's try not to materialize the states. Let's try to keep the evolving states live and die on cache. Let's never materialize on global memories. And by doing this, you save the read and writes. And by doing this, you get a much better arithmetic intensity. But such strategy have a cost because the cache size is limited. The cache size is small, and which means your state size will be small. So basically, you keep the states live and die on cache, never materialize them. But the size of the states or size of the independent evolving states will kind of bound it. And which in return will bound the arithmetic intensity again. I will show some numbers here. If you look at H100s, the cache size for each streaming multiprocessor is around 500 kilobytes, which means the independent state size will be at a maximum of 256 by 256, which will in return bound your arithmetic intensity below 100. So we have some way to get around this, but so we have some way to improve the arithmetic intensity, but it has a limitation. It's not a cure. It's just a pending fix.
Yeah. Do you think it's the main limitation, the size of the shared memory? Because if you
Yeah, I think
some
so.
of the up and coming chips like Graph Q, the chip, distributed graph, we basically say if I just make the one
Yeah.
to infinity or like pick it out. Yeah. This is based on what you say, this suggests to us that this design actually makes even more sense for linear attention model like
So what I would say that the shape of GPU influence the shape of RNN. And because RNN has limited share memory size, that's why if you look at DeltaNet, if you look at Mamba, the high dimension 128, the state size is around 128 by 128. And if you are in another universe where the hardware is not GPU, something like graph, maybe the architecture might be very different. The third aspect is that when we think about such mental graph causal over time, these are all designed for 1D causal sequences, like posing a per token causal mask. But there are a lot of data structure and does not like this, like the images and the videos, especially long videos. So how you gonna use such RNN for this data? So I went over kind of limitation or properties or features of the current RNNs. And it might be a limitation, depends on what you use them for. And I think this image describes a mental model of the fields quite well. In that designing RNN is like dancing in chains. There are so many limitations, so many constraints posed from GPU. You need to care about parallelism, you need to care about arithmetic intensity, you need to care about this and that. So now you don't have too much space to design. You have so many constraints and you don't have too much space. And I guess that's one of the reasons why paper in the fields also looks beautiful, because you need a lot of good designs to get around these constraints. But however, if you really cares about infinite sequence length, if you want to use RNN for infinite sequence length, you probably need large states. Right? You want a state to memorize a lot of tokens, memorize a lot of informations. And you probably need a nonlinear states. I don't know. You probably, I feel linear states or linear recurrence is a very small design space. And you definitely need to care about efficient trainings. And I think it is simply possible to get all of these 3 points in current design space of RNNs. So how to get all of them straight? And I think that's probably important for RNN for infinite sequence length. And which I will tell you in a few slides. The solution is actually quite simple. And the idea that to get something new, you need to give up something old. And what to give up on RNN to get all of this through. The idea is actually very simple. What to give up. And what I chose to give up is per token recurrence. I chose to not to update the states every incoming token, but instead do large chunk recurrence, update the states every 1,000 token or even every million token. And that's the idea. Give up the per token recurrence, instead do large chunk recurrence. And empirically, which I show later, the chunk size is around 1,000 to 1 million tokens, which means you update your RNN states every 1,000 tokens. And by doing so, you can have some parallelism, even if you are doing nonlinear states, because you have parallelism within the chunk. And by doing so, the arithmetic intensity change a lot. It's bounded by the minimal state size and minimal chunk size, and which can be increased to several hundred, even 1,000, if you have a large states. And also by doing so, it's naturally designed for blockwise causal mask. Because you update the states, suppose every 1,000 token, you read out the states every 1,000 token. It's designed for like block causal mask. So that's the key idea. And when you summarize, it's basically doing a trade-off. You are trading some recursive steps for more parallelism. Or I would say you are trading you give up some recursive steps for more flexibilities, for the flexibility to play with large nonlinear states, and for the flexibility to try out different RNNs. And also a very interesting detail that when you do this large chunk recurrence, you can get away with pure PyTorch programming. You don't need to write a good trading code before you do any experiments. You can use PyTorch code to run efficiently and to let you try some crazy complex ones, like the TTT end-to-end. So also in the history, a lot of people actually did chunk recurrence over the time. And I think they do it for different motivations, I think, but might be wrong. Okay, So after talking about this general idea of large chunk recurrence, I want to talk more about technical details and experiments. And before I talk about technical details, I want to give a background on what is testament training and what is means for using testament training design RNNs.
Taking a step back doesn't mean now that the state lives not in the L1 cache, but in the.
Yeah, no, you don't need to.
You don't need to.
You don't
So
need
you
to.
can make it as big as you.
Yeah, as big or small. Yeah, basically the arithmetic intensity, if you don't keep it on cache, it's bounded by minimal of high dimensional chunk size. And the chunk size can be wrong.
That is the feeling. Okay.
So let me talk about some backgrounds on testament training and how to use it for RNNs. I think the word testament training might confuse a lot of people because people think of this as a training algorithm. But when you use it for RNN, it's not a training algorithm. It's an idea of perspective to designs. And if I want to summarize, it means RNN states updates as a step gradient. It's a little bit abstract. I'm going to talk more details. So to get started, I want to talk about attention to get some more iterations. Let's talk about Harmax attention rather than softmax. It's Harmax, it's much easier to understand. Suppose you have a key value cache of 4 tokens over here. And when you have a query token came in, when you do the decoding, what are you going to do? You're going to look up every previous case and compute similarities and get a best match and extract the values. So that's what you do for Harmax attention. And if you look at the KV cache as a data set, as a mapping from key space to value space, there are 4 points, 4 mappings, 4 pair mappings. Then Harmax attention, and the key value cache defines the map. Suppose there are space of k and space of values. There are 4 data points on this data set, and the key value cache defines the data set, defines the mapping. And the Harmax attention does is when it's a neighbor on this data set. You use query to find the nearest k, the best match k, and get the value odds. And you can argue that maybe softmax attention does 100 nearest neighbor or top k nearest neighbor and get a weighted average current or something like this. And if we look at a Harmax attention in this way, in this key value cache mapping way, then the question will come at how are you going to compress a KV cache into another neural network? I think the answer is kind of straight. The answer is that let's call it f dot. And then you can directly define the loss we want to minimize is you put a k as inputs and you hope the output is close to v. Because the KV cache is a mapping from K1 to V1, K2 to V2, K3 to V2. And you hope you pass K1 as inputs, you hope the output is close to V1. So that's the idea. Given the KV cache of a kernel sequence, we treat it as a data set. And to compress them into a neural network, you just use this KV regression loss to minimize the neural network. So you define a network, define an objective function, and you train this network. And then after the training, the network will compress a mapping from K to values. And another question is, when a future query token came in, what you do is you put Q as inputs and you get outputs. This is like queries.
Why do you, so for this and like all the delta net, I think they assume that Q and K live in the same space, right? Why does that assumption make sense?
I mean, I don't think it's so let me answer more straightforward way. More straightforward answer than that. When you do attention, when you do QK dot products, they lie on the same space. And the attention never assume QK on the same space, right? The model will try to learn such an QK dot product makes sense. And in this case, yes. Then this phosphorus function, this compression help you compress K to V. And when you query this compression use Q, the network will learn to align QK in some sense.
I see. So you're saying that because we are calculating the attention matrix with QK, which inherently means like maximizing it. Like 1 just means extracting the like respective D.
Yeah. If you look at the Harmax attention, it basically does this, right? It basically says we're going to use query token and to find one nearest neighbor on this space and get the value out. That basically basically assumes QK are in the same space.
I have a thought, which is, I think some people observe that you can just do short computation on the keys only, without short computation on code. Now, if what this assumption holds that they should be on the same space, it doesn't make sense at all to do short computation with keys without going from positive Q. They're just moving the space now.
I don't think we'll change the space. Short convolution is that you mix in some case. You make the K closer to previous case. It's still on the same space.
Yes.
But fundamentally, I don't think QP need to on the same space. I actually don't. I don't think that abstraction is important.
Can you just know that to imagine deep learning? The Q would be nice enough.
Yeah.
To the tree.
Exactly. Yeah. And I think this basically give you a way to interpret. It's not working this way. It's give you a way to think about attention and think about RNN. So, given this idea, basically to compress KV cache, you just train a fast weight neural. You just train another neural network, and typically we call this weights as fast weights because it's adaptive per sequences. Or this weights can also be a RNN states. It's a similar concept. It's trying to memorize current sequences. And I'm going to show this again is the same graph, but I draw differently. In that you suppose you have a key value cache you want to compress. You'll pass a K to a fast weight neural network. And this fast weight neural network do some prediction. And we call this prediction as retrieved values. And you compute a pairwise loss or pairwise similarity between the retrieved values and values. And you use a lot to do gradient descents. And after some gradient descents, you hope this fast weights or this neural network memorize the key value cache. And yeah. Okay, so here are some ideas to compress KV cache. And what I'm going to tell you that all these linear RNN are actually already doing this already on their state update period. And then let's look at them. And let's start from linear attention, the most popular and simple form of current RNNs. And here I have some ingredients. It's fine. You don't read it. That's so fun. And for some people, you want to read it this one. So what I'm gonna say is linear attention has a state of a matrix state. S is a state. It's a D by D matrix. And the state updates is the run clone updates over here. Every time run clone updates, every time run clone updates. And now if you think about this state as a weight of a linear neural network layer, this linear neural network layer, then the memory readout is a model forward pass. This memory readout is a neural net forward pass on the query token, which is basically what we showed on the previous slides. And now the state update is actually one step of gradient descent on this linear neural network layer. Some equations here on what loss under this loss. Whereas FS is a linear neural network layer. You pass the K as input. You compute dot product loss between the predict value and the value. Basically, this loss try to align the prediction with the values. And the one step of gradient descent, exactly this state updates. So some very simple equation, but it's fine to not track them. You just feel the intuition is fun. And not a coincidence in that if you look at Mamba 2, it can also be interpreted in this perspective, where it just where the state updates is slightly complex with one scalar decay. And this can be interpreted as adding a weight decay over here. And if you look at DirtNet, it can also be explained the same way. The state update is slightly complex, but if you look at the training objective function, it only changes the training objective function from active dot product loss to L2 loss. So basically, I go over some concrete examples, and this is all told, all summarized by all previous papers. And I think the testimony training paper basically summarizes it. And my understanding of this is that by looking through this lens, by looking through this perspective, the idea of testimony training gives a big design space for new RNNs. It cuts the design space in 3 axes. For example, when you design RNN, you can start by designing a fast rate function. In all 3 previous examples, the fast rate function is a linear neural network layer, but it can be anything. It can be an MLP, or it can be a transformer, or it can be anything. And typically you can use FW to represent the fast rate function. The second step is that you want to define a training objective to train this fast wave function. In all previous example, we showed the training objective is to memorize the KV cache or to associate the K with values. But you can do whatever you want. You can use maximum prediction. You can use diffusion law. You can use MAE loss. You can do whatever you want as long as you can define on current sequences. So as long as you can define on its loss function with respect to fast wave function and your input. The third design axis is what optimizer you're going to use to train the fast wave function. As three previous examples, we showed basically gradient descent or gradient descent with weight decay, but you can also use whatever you want. You can use momentum, you can use one, you can use NM, whatever you want.
I had a question about this this fast wave function that you learn the mapping from the keys to the values, right? So is the motivation of that it's basically just to compress this these like vectors into just so that they will not take up as much memory, or
So that's one because is that suppose you have a 1 million token KV cache.
sure. Sorry, I think your audio is cutting out a little bit.
The audio is low.
I think it's okay now.
The size of the KV cache is much less.
Sorry, the audio's I can't the audio is not coming through again. I'm not sure what the issue is.
Is someone else talking?
Somebody has their mic on without scaling the
I think
echo.
it might be, we can also hear noise from your end as well. That might be the problem.
Well, I think it's just it's working now.
Is it working now? Maybe because how about now?
I think it's okay, right?
Okay. So I think that's one way to understand is compress the key value cache into the fast waves. And when the key value cache is large, it's compressed.
So if you have this learned keyed value mapping, then it basically what halves the amount of memory required. You're not learning the keys are not learned, so you're learning the mapping to an output value.
So yeah, that's compress the mapping into the fast wave function. And I think that's the point of key value cache. Maybe that's the point. Maybe that's the point. So one point of a key value cache is a mapping from key to values. If you look at the attention as a Harmax attention. And on
Okay.
the side, key value cache is large enough, it's compressing the key value. But I think it's only an interpretation and it's not what's happening really. It's just a way to think about new RNNs.
Okay.
Okay. So the idea of a test training opens a big design space for RNNs. It have design space along three axes. And if you look at the design space, it has some shared space with the linear RNNs. And the majority of the space is nonlinear.
Generally, is a fast wave function a single layer?
It can be any.
Do you find that, or have you tried like multi-layer versus single layer? And
Yeah, I think it can be anything. And to answer the question, if multi-layer MLP would be better than a linear layer in terms of fast wave, it's harder to answer. Because the design space also depends on some other stuff. Yeah.
Imagine if you design a good enough optimization algorithm with a small chunk, probably will basically maybe nothing.
I don't think so. Yeah. It's a co-design between the if you want the algorithm to be hardware friendly, also you want an algorithm to have some nonlinear, some large states.
I see, so you can have like tiny layer, like this is not like the current layer,
Yeah.
like a tiny layer. You can
use the loop layer. So if you look at the majority design space, the test time training for it's nonlinear arms. And I think to be able to train efficiently on the nonlinear arms, currently the most promising way is large chunk recurrence. So here's the background of customer training. And now what I'm gonna show is I go over this design space, do some exploration, and find some architecture. I want to go over some experiment results on this architecture. So what do I find? What I found kind of stable is a sweepable MLP as a phosphate. It's a common MLP used in language model, and I have 3 memos. And I use the same customer training objectives as all the linear RNN I showed before. Basically memorize key value cache. And for the optimizer, I mostly use gradient descent, and I do find some other optimizer are used.
Let me clarify. So this uses the MLP layer. Or you have a separate sweepable MLP, and then now the sweepable phosphate.
Sweepable phosphate, actual. It's actual.
So this MLP layer which is sweepable.
Yeah.
And then a sweepable like now attention like
Yeah. So this sweepable is only to memorize the key value cache, not to memorize the pre-trained knowledges. So finally, it looks something like this. You have a MLP phosphates, sweepable MLP phosphates. You're going to do a gradient descent on the MLP phosphates every lot of token, every 1,000 tokens, something like this. And after gradient descent, you're going to normalize the weights. That's probably the most important operation I do for stability. And to do the readout, you're going to curve the near spy updated weights. And this is like a blockwise cosmos.
Is it a single gradient descent step? Because
Yeah.
for
So-
normal net, for not fast weights, we take
Yeah.
many, even to learn a single like key value, like, data set.
Yeah.
Even if you take like not SGD, but GD, you still need many steps.
Yes.
Right?
So you're asking here, how many gradient steps I'm doing?
Yeah.
So finally, I'm doing 1.
Mhm.
I tried 2 or 4. I think larger than 4 is unstable, and 2 or 4 does not give me any benefits. I don't know why.
But that's very different than normal weights training, right?
I think it's very different. It's because there's a second order gradients alter loop training the whole thing. And I don't know why. Maybe stabilities because we have a lot of recursive steps over the same KV and the phosphates. Probably it's unstable. Yeah, I don't know why. We can.
A related question. So this training is online training, which means, for example, the first few tokens, you only saw them at the very beginning and you don't retrain on them again
Yeah.
in the future.
Yeah.
This feels to me very unintuitive as you will for sure forget about the first tokens.
Yeah.
Is this like a on purpose injected locality or
Yeah.
how do you view this?
So I understand your concern. So a lot of people ask similar question is, you use a phosphate, you train them online, your KV cache. Suppose your KV cache have 1 million tokens. You do a gradient descent for every 10,000 token, you do probably 100 gradient descents. And for the final phosphates, is the phosphate be able to memorize the first 1,000 token? Is there some locality bias in the gradient descent? I think the answer is generally actually the locality bias is very weak. It's much weaker than you thought. And I have 2 empirical evidence, not shown on the slides, but again, show very roughly. One is, if you look at a simple QA benchmark, it's about asking the language model some knowledges, some long tail knowledges. So it's a benchmark to develop pre-trained language models. Ask a lot of very weird questions like, who is the championship of 1999 blah blah context? And you can imagine during the language model pre-training, language model definitely sees such a, but I don't know where. If you think about the 10 trillion pre-training token causally over time, the language model during pre-training is also doing gradient descent causally online. And after the language model is trained, you evaluate on the simple QA. It's like a needle in a haystack, but you're using your whole training data sets as a key value cache. And the model does relatively well. The knowledge is on the simple QA benchmark probably lies possibly anywhere on the pre-training data. That's one evidence. Another evidence in that if you use such architecture, suppose you train a dirty net to do random string reversal synthetic task, or to do some task where you, I will be more precise, to do a random string reversal task. Basically, you let dirty net read through a random string and copy paste, but in a reverse order. In a reverse order, where the first few tokens will be pasted the very last time. If you look at a per token accuracy, it's flat. It's not saying later token if gaps.
It is fundamentally to this, or just because
Empirical.
my interpretation is if you want to gradient descent, you're like naturally have a inductive bias.
I think you have a locality bias, but the locality bias is not as strong by looking at the empirical experiments.
And then we call it phase recovery.
Non-gated ratio.
And again, yeah, to emphasize this speaking.
So for locality bias, I'm going a bit too far, but my take is that it's not that strong. Probably not a big problem. So another thing I want to be clarified is you need to think about the data topologies. When you think about such chunk recurrences, it's designed for data topologies of sequence of a set. When you do chunk updates, it ignores the topology of all the tokens within the updates. So basically it's processing a set. And when you do updates multiple times across sets, so you're basically assuming data topology of a sequence of sets. And not all data are sequence of a set. Probably none of the data we see today on the sequence of a set. So to handle this data, so you need position encodings, and also you need a window attention to help you model topologies within a set. So through this paper or through all the experiments, it's a hybrid architecture where we have a window attention or sliding window attention to handle locality or window topology within a set, and a cross-check set is causal. And so summarize, it's a hybrid architecture. One thing is for data topology, another thing that you want to use RNN for long-term memory and attention for localities. And such strategy also being used in a lot of previous work. And now I want to go to experiments. I want to go experiments probably very fast. Probably I will show the novel view synthesis experiments because a lot of people don't understand it. So I'm going to show you to use this model to train on a type of task, type of retrieval task. And what is the output of this task going to look like? It's going to look like a video like this. And the definition of the task then, I will take 100 images of this room, and I will pass these 100 images to the RNN. Let the RNN read through these 100 images. And after that, you need the RNN to render the room again. So give a lot of input images, compress into states, and render the room again. So it's a task that is a retrieval task. Because to render the room again, you need to find you need to memorize relevant patches. And it's not a single hop retrieval. It's around 2 or 3 hop, or typically highest, because you need to do 3D preserving retrieval. And to do 3D, if you have some computer knowledge, you realize at least a 2 or 3 hop. Second, then, it's a retrieval with compression. What does that mean? When I give you 100 images of this room, probably this table or this patch will be visible maybe 10 times. And you only need to compress into 1 token. You don't need to keep all of them. So it's a retrieval with compression. And you can play with different rooms, different number of images to make the task harder and harder. So, and the reason to use such retrieval task then people believe RNN is better at retrieval. And retrieval the task than RNN is far more behind in attention. And that's why I'm using this task to stress test. Another reason that this task like golden metrics. So it's kind of easy to give you some conclusions. Okay, let's look at this figure. The y-axis is the performance, higher the better. The axis means number of images or number of tokens. And the right line is our RNN. And the blue line is full attention. Remember, full attention never does compression. It directly do the selection and then retrieval. And so we are now very behind full attention. That's the table. At around 10 times faster speed because it's a RNN linear complexity. And this white gray line is perceiver attention. It's kind of using attention for compression. I want to go too much detail here.
Perceiver, position encoding. No.
And when scaling this up on 1 million tokens, it's
Can you explain the second, the right-hand side plot again? Where you said it's 10x.
yeah. So where I plot a figure similar style, but as the axis means speed, y-axis performance, x-axis basically means time.
What is the size of the state of this model?
Yes, the size of the state is probably Okay, I will show you in this figure. Where the axis means 128 images or 1 million tokens, and the size of the states might be 80 megabytes. And the size of the whole model might be 300 million parameters. The size of the state is 80M, size of model 300M. And here, I think it's interesting to look at the gray line. So the gray line is previous soda. The green line is a traditional method from the graphics community. It's called 3D Gaussian splatting. It's basically using human design inductive bias to do the compression, to compress hundreds of images into a 3D representation. And you can see this RNN can learn better compression in some sense. Humanly designed inductive bias. So I probably will jump over some other experiments and jump directly to the final conclusion. I will jump over some language models. So I jumped over something because I want to take the next 10 minutes to talk about another stuff. And to summarize current stuff now, what I try to sell it, or what I give you an impression that RNN is like dancing in chains. So many constraints from GPUs, which we discussed before. And using large chunk recurrence, you cannot get away with such constraints. And because I jumped over some language model experiments, so the real take is it might also be a poison because you give up some recurrence and you are underperformed in some task. So large chunk recurrence give you more flexibility, give you more hardware efficiency, but on some tasks that requires recurrences, it underperform. I jump over this slide. And for the next 10 minutes, I want to talk about another word very related, but in a very different perspective. It's about the measure how much RNN can memorize.
One question before you move on. So for different domains like novel,
Like the images, yeah.
like dimensional, do you
Yeah.
find that you can use different, like there are different block sizes that are optimal?
Yeah.
And that, maybe the recurrent states don't need to be reused so
Yeah.
much in
Yeah.
the images because
Yeah.
there's so much redundancy.
Yeah. So for images, I think it's an inductive bias for each data topology. For images, the chunk size should be better aligned with one image. All the images. For example, when you have videos, it's image causal over time. It's better for your chunk size, it's just one image. It's better, but not fundamentally better.
What about in the language case?
I think smaller the better.
Smaller the better.
The smaller, the slower.
Yeah, but smaller is more slower. So it's a trade-off. So another thing is about trying to understand R. Okay. So one I want to start with the motivation. So when you think about continual learning, there are two ways to do so. One way is that you use the RNN to do infinite in-context learning. You compress everything into your RNN states. The other way is probably more intuitive, is every once in a while, you're going to fine-tune your transformer. Every once in a while, you're going to train your transformer end-to-end to memorize some previous knowledges. And then, why in-context learning can beat the fine-tuning ones? Why the first approach, memorize everything into RNN states, can possibly beat the full fine-tune baseline? And to answer that question, I think that we want to show how much RNN states can memorize and compare how much pre-training a transformer can memorize. A little bit abstract, but once I show this image, probably some people can understand. So this is from a primer from Alan Zhu from physics language model. What it does is it does a lot of synthetic tasks. To answer one question is, when you pre-train a transformer on a big data set, how much the transformer can memorize about the data sets? And the takeaway from that paper then, when you train 1,000 epoch on this data set, every parameter of the transformer can memorize 2 bits of knowledge about the data sets. I don't know if you guys read this paper. And another relevant paper about a year later from Meta says does similar experiments, but on different configurations, and give a similar conclusion that every parameter can memorize 3.6 bits per parameter, per bit. every parameter can memorize 3.6 bit. So this basically says, okay, if I fine-tune the full model, or if I pre-train the full model to memorize something, every parameter can maximally memorize a few bits. And now I want to do the same thing to RNN, but not pre-training, but in context learning. If you let an RNN read through some article, read through some information, how much information can be memorized into the RNN states?
Actually, I have a question about this parameter.
Yeah.
That essentially implies a given model has fixed capacity.
Yeah, fixed.
But imagine you do attention, you have growing KV cache
Yeah.
size. Doesn't mean that doesn't matter. You have to imagine as you go into bigger and bigger.
Yeah.
You will have more bits per parameter. Yeah. But that seems conflicting what this is trying to say.
Attention does not memorize. Sorry. What is the? I actually don't know why you feel it's conflicting. So this paper says, given a transformer, fixed parameter size, it can only memorize fixed amount of information. And I want to measure how much it can memorize. And the conclusion is 2 bit per parameter in pre-training. So it doesn't depend on the size of KV cache.
I guess because the attention window size is also
Fixed. Oh, you can also think that way.
I see. Okay, makes sense.
So if training a transformer end-to-end can memorize around 2 bit or 3 bit or 4 bits per parameter. And if this is a takeaway, and if I tell you, if someone tell you RN reading through one article can only memorize 0.01 bits, then you're probably gonna say RN for in-context learning is hopeless. That's basically the motivation. So, but if RN can memorize 100 bits per RN states, it basically says in-context learning is very hopeful. Okay, some details before I jump to the conclusion. So how to measure how many bits RN can memorize? I also use synthetic data sets. Very similar to the meta paper is you can synthesize a lot of random string like this, A, B, C, D, something random string, and let the RN read through the random string and paste the random string. And depends how well this RN can copy paste a very long random string, you can measure how much RN can memorize about this random string. Very similar style to the work, but the only difference is one is in pre-training, one is in context learning. And when I scale this over multiple scales, I get a kind of consistent measures where the x-axis means RN states with delta net. The y-axis means how much information it can memorize after reading a random string through it. And the curve is around 2 bits per state. And the larger scale experiments I run and the smaller scale experiments I run have flops around 1,000 differences.
I think go back to that. So earlier we measured the transformer place per parameter is we measured parameter of the model.
Yes, parameter of the model. Yes.
Yeah, now we measure
Parameter of the states.
But obviously for RNNs, is there a similar analogy if the parameter per weight exists, or that doesn't even matter in this case?
So for the in-context learning case, it doesn't matter for the parameter. Because the parameter never know what a random string gonna be in the future. Only the RN states have the information about the random string.
But then in the tension case,
Yes.
would it make more sense to measure this per KV cache bits?
It doesn't make sense because the size of a KV cache is increasing. There is no concept of compression.
Maybe if you do like sliding window attention, you basically throws away the KV cache, then it becomes meaningful metric.
They become meaningful, but I think the measure will be very low because sliding window cannot retrieve long. So let's take the time to think about this conclusion in that we have our read-through random string, it can memorize around 2 bits per RN states. This number 2 doesn't matter. What it matters is that the number 2 is close to number 3.5, close to the number 2 Allen Drew measure. It basically says the in-context memorization capacity is similar to pre-training memorization capacity. And then another interesting point is that here, the RN only reads through the random string once. But what Allen Drew and Jeb Morris measured is pre-training on the data around 1,000 epochs. So another thing I want to clarify in case I don't mislead you, here I'm caring about noisy retrieval, now precise retrieval. So when you do the random string copy paste, the accuracy around here is around 60%. It's not precise, not precisely memorized every previous bit of information. roughly how much you can memorize.
And in the transformer papers, is it also like noisy retrieval or is it the
It's
precise?
so in that case, I think both. Both. So for example, you can have a large data set and train different size model. And for smaller size model, you even at 2 bits per parameter, the retrieval accuracy is not 100%. But mostly precise. So for example, I go back to the Allen juice.
Yeah.
Yeah.
So this is precise, like for precise retrieval.
So what he shows that when you train different size model, you on different size of data sets, a lot of the envelope lies on around here, around 2 bits. But for some other points, I don't think it's precise. For point below the curve. But for points on the curve, lots of them are precise. It's not all of them are precise. It's a little bit detailed. If you do the experiments, you will realize.
Yeah. And do you take that into account when you say 2 bit per parameter? You said that it's like if you have only 50% accuracy, then it's like half of the sequence information.
The equation is not exactly that, but some sort of some sort of.
This notion of memorization is obviously in connection to social recall.
Yes.
Which is it's an interpretable number people can relate. But in practice, do we really care about retrieval that much?
Yeah. So the thing we want to care about retrieval. Sorry. The thing I care about this retrieval is about I want to measure how much you can memorize. And the thing, if I can find a way to measure how much you can learn, problem solved. But measure how much you learn is so hard. So we can only measure how much. I can only measure how much you memorize.
Would it be imagine you have a magic wand with any metric wand? It seems to me it makes more sense to think about generalization than memorization.
Yeah, but generalization is much harder to evolve than memorization. That's the problem. I definitely want to measure it. Tell me how much RNNs you need to learn math flow.
Learn the scale.
Learn the scale, but it's just much harder to measure. And so here the conclusion I draw is about in-hand memorization compared with pre-training memorization rather than learn.
Here, does the order of retrieval matter?
The order of what?
Does the order of retrieval matter? Let's say you're not copy pasting, but actually, let's say you reverse the string, right? Because for this type of like RNN style retrieval, actually the quality of retrieval for at different locations could be different, right?
So two questions. The accuracy of the retrieval, does it depend on the positions? I think for dirty net it doesn't. If you look at the accuracy for the random string copy, it's flat. And if you do reverse retrieval, it's flat. Second question, or your first question is retrieval 2 bits. If what do we do about reverse retrieval? It will be way below 2 bits because you need probably part of the states to do the reversing and part of the states to do paste. I don't know if you get it. So for copy paste, probably you only need a 2 circuits or 1 circuit, and all the states can implement in that circuit. And for reverse retrieval, you probably need a way more number of circuits. And you need some layer of the RN states implement circuits 1, some layer implement circuits 2. So when you measure the whole bits, it's way below 2.
Okay, yeah, that makes sense.
I try to measure. I didn't get a consistent measure, but I can tell you I measure something maybe between 0.5 or 0.6. But it's not a consistent number.
This reminds me of like Simran has a paper like I just like the model twice.
Yeah, retries.
Yeah, it's very good. Yeah, twice because as a result, if something comes later, the second task can look into what's happened.
Yeah. So for this measurements, you can also retries. Before it converges much faster to 2 bits. But the selling is also wrong.
It's not the same, but you just have baskets.
Yeah. Is that when you train the network for 1 hour, it can already memorize 2 bits. Let's have a question on the chat.
The phone task.
Yeah, I think I'm mostly done. Yes, and another thing I want to see is I want to jump through the details. Is before I leave, I think I might leave a. I need to clarify again. This is nonlinear retrieval and it's a random string, and it's memorization. It does not translate to real data and does not translate to in-class learning. But I do believe if you make an RNN that is very good at in-class learning with a large states, you can possibly go to infinite context. And that's a potential way to solve continual learning. And how to get there, a lot of research question today. And I want to thank all the collaborators on the